Okay, guys. Hi. This is a video, your video lesson for Tuesday, February 21st. You guys, this video is a little bit longer than what my normal videos are. You are expected to watch the entire video. I'm putting a lot of information in here, but also I'm kind of running through every activity with you this time instead of asking you to do things on your own. You're going to have two homework assignments. Number one, if you didn't get all the video watched in class, then I want you to finish watching it on your own. Um, I can't remember if tomorrow's an A or a B day, but I want you to finish watching the video. And then there's a worksheet that you're going to have for your homework assignment. Okay. All right. So let's start first of all with your scientific argument. Since we didn't have school last Thursday, you all still have your scientific argument. And I want to talk to you about that a little bit real quick before you hand it in. So let's review it. And then if you need to, you can revise so that you can get 100%. All right. So, first of all, we had the question, did the methane lake on Titan freeze or did it evaporate? And the answer is that the methane lake on Titan evaporated. So hopefully you got that right. What I'd like you to do is I need to have you make sure that you have where you used race and you restated and answered the question. So you should have the methane lake on Titan evaporated. Now, if you didn't, I want you to revise and watch this video in this part before you make any changes on your paper, okay? Because I'm going to give you some specific directions for revising. But if you said the answer was evaporate, then let's just check your answer and make sure that you have everything you're supposed to have, okay? So you should say the methane lake on Titan evaporated. And then we need to have some evidence too that we cite to support it. Okay, so let me show you. It doesn't really matter what order you put these in, but this is how I presented the information. I used evidence card D first because to me, this is the strongest piece of evidence that we have. And remember, you always want to start with your strongest piece of evidence. But evidence card C is also very strong. I want to use evidence card D first and then incorporate evidence card C because these two evidence cards together really, really make a very super strong statement. If you didn't use both of them, I would rather that you use evidence card D, although you kind of have to use C. And if you used C, you could sort of infer that there's more energy going in because of the summer. So here's what I wrote. I said evidence card D supports the claim that the lake evaporated because it says that there's an increase in kinetic energy in the summer. The information that I have in red, this is the C part of race. This is where I'm citing my evidence. I asked you guys to write a summary about the evidence cards. And so this is just what I have in this summary. I don't want to repeat exactly what my card says, and I want to make sure that I'm very careful about summarizing the information and not sometimes we need to infer, but this one is pretty direct. It says because there's an increase in kinetic energy in the summer. And then I'm going to tie in evidence card C. And I said, according to evidence card C, it was summer in 2007 and 2009 when the pictures were taken. So I've cited my two evidence. Now I can use the E part of race where I'm explaining why my evidence supports my claim. And I said, key concept 8 says transferring energy into a substance increases the kinetic energy. And then remembering I need to talk about what happens on a macro scale and a molecular scale. An increase in kinetic energy results in an increase in the molecule's speed and FOM, which means the methane, I spelled methane wrong there. The methane went from a liquid to a gas. This is evaporation. So I've discussed what happens on a molecular scale, and then I came back and talked about what happens on a macro scale, that we went from a liquid to a gas. So this is a great first part of my scientific argument when I'm supporting a claim. Now I need to come back and talk about what evidence can I use to refute the claim. So I'm going to say use evidence card B to refute. Evidence card B is refutation because it says it isn't cold enough for Titan for methane to freeze. A couple of you guys at parent teacher conferences, I was asking you what evidence card you used to support that the lake evaporated. And a couple of you guys said that you wanted to choose evidence card B to support. Now, I'm going to tell you why it doesn't support, because it doesn't say anything about evaporation. It doesn't say anything about energy going into the system. All it tells me is that the summer temperatures are not low enough to freeze methane. Okay, so this is actually the best card to use for a refutation. Again, my red print on there is to show you for citing my evidence, and then here's why. Let me go ahead and explain the evidence. The kinetic energy isn't low enough to decrease the molecule's freedom of movement, and the methane cannot change from a liquid to a solid. So remember, I'm refuting it. I'm telling it why it can't be that. I'm not supporting or using it to support and say, well, it can't be that, it has to be this. I have to argue against a claim. So that's why I'm using evidence card B. Did we use evidence card A at all? And the answer is no, we didn't, because evidence card A just gives us information. It tells us what the temperature was, and that's it. We don't have any evidence about, it does say that it's summertime and it's very cold, but it's really fluffy evidence. It doesn't really tell me that it was summertime during the time that the pictures were taken. It doesn't say anything about energy going in. So this is my weakest piece of evidence, and I am not going to use it at all. Okay, so let's go ahead and have you guys hand in your scientific arguments to the white basket to be graded. That should be at the front of the room, or it's on top of my rolling table. So whether, I can't remember if I put that in the front of the room or if it's off to the side, but you can go ahead. If your argument is similar to mine, it may be different. You've got different writing styles than I did, but if you use the same piece of evidence as that I used, go ahead and hand it in. Now, if you didn't use the same pieces of evidence, I want you to revise it, and you need to do so in a different color. And I'd like you to have those due to me tomorrow at the beginning of class. Okay? You're not going to have any time tomorrow to finish writing those. If you would like to do that now and then finish watching the video and working through the lesson for today, you can do that. It shouldn't take you very long to revise. Please remember to write in a different color. If you need to just attach a notebook paper to your original, I want to see what you had and what you're going to change it to. So please make sure that I know that this is a revised copy, okay? You can stop the video, do what you need to do, and come on back. Okay, I want to talk to you guys real quickly about what I have planned for the next couple of weeks. So today's the 21st. I'm running through lessons 1, 2, and 3 in chapter 3. And it seems like it's going to be a lot, but we've really talked a lot about the topic of chapter 3, which is the level of attraction between molecules. We've talked a lot about that already, and I did that on purpose because I wanted to bring that idea up and really help you guys think about that before today. So I think we'll have enough information that you guys will be able to take your mid-unit assessment tomorrow. And those of you that are going to revise, if you wanted to revise tomorrow, I would give you the opportunity to do that as well too if you finished with your mid-unit assessment early. And then if you score 90% or above on your mid-unit assessment, you can use that as your end of the unit assessment, and then I will move you on to an individual activity. And those of you that don't score 90% or above, it will help me identify what areas we need to review. So on Thursday, those people that just need to review will do lesson 3.5. And those of you that move on to the individual assignment, I'll give you that so that you can work on that for the next couple days. And then don't forget, Friday is our field trip, so nobody will have school. We're going to be gone all day. If you have any questions about that, ask your guided study teacher, ask your advisory teacher. You can certainly ask Mrs. Scanlon to find out. But the most important things that you remember is that you need to bring a sack lunch. Okay. And then next Monday and Tuesday, these are important days. I do not like giving tests on Mondays. I don't like that at all, but I have to because we need to really get going. And with the snow day and our field trip and just everything, we really need to get going. So we're going to have the vocabulary and key concept test on Monday, the 27th. And then on Tuesday, the 28th, will be the end of the unit assessment. And so, those of you who are working on the individual assignments, the individual activities, you will take the vocab and key concept test on the 27th, but then you'll have one more day to work on those individual activities on the 28th. And then Wednesday, we have a really fun nitrogen lab planned. I'm going to have some liquid nitrogen. We're going to be working just some fun things. Liquid nitrogen is pretty dangerous, so a lot of it I will be showing you, but I'm going to have some people come up from the class volunteer, and we're going to do some fun stuff. And then we'll start chemical reactions on Thursday. Okay, so just kind of, we're almost to the end of phase change. This is what we've got going on. That being said, let's go ahead and get started with lesson 3. So I want to remind you about your pop quiz. Do you remember? This was on the back of the first page. I had this table here, and I asked you guys to fill in how the molecules behaved in a solid, liquid, and gas with reference to their freedom of movement and the attraction between the molecules. And if you remember, in a solid, the freedom of movement between the molecules is really, really low. So imagine that you're putting your two hands together and rubbing your fists back and forth. And the freedom of movement is really, really low. Those molecules cannot move around each other. And the reason why is because the attraction level between the molecules are really high. Let's jump to a gas. The freedom of movement is really high for a gas, meaning that this is where we would put our fists and, like make them hit each other and then come back and move out. So our gases are moving very quickly. They've got high freedom of movement. And the reason why is because their level of attraction is very low. If they hit another gas molecule, they'll just bounce right off. They're not really attracted to another gas molecule of that substance. And of course, in the liquid, freedom of movement and level of attraction is medium. So we've talked about this before. You guys seem to understand it. We're just going to do a little bit of review about that, okay? So today we're going to observe two liquids. And one is a bottle of water, just regular water. And the other one is called isopropanol. It's rubbing alcohol. And I want you to note whether the same energy transfer will cause them to evaporate. So if we're just making an observation, we're looking at them. They're both liquids. They're both clear liquids. And so even though they have some of the same physical properties, we want to see if they have some of the same chemical properties. Not chemical properties. That's wrong. I'm so sorry. I want to see if they have the same physical property of what is their boiling point, what is their at what how much kinetic energy is required for them to evaporate. Okay, the two liquids are going to start off at the same temperature, and that's just going to be room temperature. And they're going to be in the same environment. Nothing is going to be nothing is changing between one or the other. So that means that the same amount of energy from the air will be transferred into each liquid. Okay, let's go ahead and watch this video. And I think, yeah, I'm just going to delete the mute, or I'm going to mute it. All right, so they have one drop of each one. The students are going to draw a circle around the drop so that they have a reference point of how big the area where the liquid was placed on the paper towel. And we're just going to kind of fast forward the time. It's time elapsed for 5 minutes. And you can see after 5 minutes, we're making some observations between the water and the rubbing alcohol. and you can see that the rubbing alcohol evaporated faster than the water. Interesting. So now I'm going to ask you guys to just kind of think about that. Why would that happen? Why would that happen? So we have a new email from um, Galileo. Do you remember the question forum on that website, the Universal Space Agency's website? Well, somebody wrote a question to us and they said, I read your findings about the lake, but I'm confused about the argument that the lake evaporated between 2007 and 2009. The evidence shows that Titan first started getting hotter in 2002 when summer began, but the methane lake was still liquid 5 years later in 2007. If the temperature increased starting in 2002, then energy was being transferred into the lake. Why then hadn't it evaporated by 2007? It's a valid question. It's a good question. This person is asking, listen, if we know the temperature started increasing in 2002, and we know that temperature increases because kinetic energy increases, then why did it take so long to evaporate? So let's take a look at the timeline again. The forum user is confused because summer started in 2002, and when the liquid lake was photographed in 2007, it was still liquid. So if kinetic energy is increasing, why did it take so long for it to evaporate? Now, we don't know exactly when it had evaporated. It was sometime after 2007. It could have been literally a month after the photograph was taken. We don't know. But the point is, it didn't change for 5 years. How come? So that's our chapter 3 question. And I want you guys just to start thinking about the sim. We're going to come back to the sim again towards the end of the lesson, and I want you to consider it again. But I want you to think about what we have observed about energy and phase changes in the sim. Does adding or removing energy in the sim always result in a phase change? So when we cut to the sim page like this, and I say to you guys, okay, go ahead and add energy in. Do you push the plus sign or the minus sign one time, or do you have to push it multiple times? And the answer is you do. You have to push it multiple times in order for a phase change to occur. Why? Why does it take so much more energy? Why does it take a lot of time, a lot of energy in order for a phase change to occur? Let's find out. Over the next lesson, it says 2 lessons, but I combined everything just in this one. We're going to use our observations to answer this question. Why does an energy transfer not always result in a phase change? Dr. Flores thinks this article may be helpful in answering the investigation question. It discusses how difficult it can be to change some substances into a liquid. So you guys have this liquid oxygen article that you should have gotten from your sub as soon as you came in the door. I'm going to have you guys write the investigation question at the top. So I would like everyone to have a hard copy. I'm going to read the article. You guys follow along. I'm going to talk to you about the annotations that I want you to mark. I'm going to show you the annotations I want you to mark. Let's start first of all by writing that question if you haven't yet. Please put your name on your article too, please. Your name and your class period. And I want you to write down, why does an energy transfer, and then underline, not always result in a phase change? And then let's go ahead and work on some annotations. Okay, so this is the first paragraph. In your daily life, oxygen is everywhere. It's in the air all around you and even inside you, traveling from your lungs to every cell in your body. You probably think of oxygen as a gas because that's how you encounter it, but it isn't always a gas. Oxygen can also exist as a liquid with a beautiful blue color. However, you'll never see puddles of liquid oxygen on the ground, and you can't buy a bottle of liquid oxygen at the store. Oxygen is very different from water, the most common liquid on Earth. Scientists can produce a liquid oxygen, but it isn't easy. Why is oxygen gas all around us while liquid oxygen is so rare? So this is just an introductory paragraph. It doesn't really answer the question, why doesn't a phase change always occur? So we don't have any annotations here. Let's go ahead and move on to the next paragraph. Before we do that, I have a visual reference I want you to consider. So I'm going to show you this video. Do you guys remember when we did the magnetic marbles? Well, I'm going to show you a video in which there's another type of magnetic marble. So the marbles on the left are the marbles that you guys encountered in your little plastic sandwich containers. And they actually have a pretty weak attraction, meaning the magnetic attraction between them can be easily broken. And you guys showed that, you demonstrated that, because when you shook them back and forth, they were easy to overcome that level of attraction. But the magnets on the right are actually a stronger magnet. Now, the level of attraction between molecules is not magnetic. Remember, this is a model that we're just using to kind of imagine how that acts. So let me show you the video. I actually want you to listen to it. So see, not a whole lot of kinetic energy is required to break that bond between the weak, but the strong ones stuck together. I'm going to show you that again, just because it's fun. I want you to see it again. I'm going to mute it this time. It's the same amount of kinetic energy that's being placed into each one, but the weaker marbles, that level of attraction is easy to overcome. It wasn't easy to overcome for the stronger attraction. So it's actually a good thing for us to think about, and I'm going to bring it back up here as I read. Okay, let's read the second paragraph. First of all, the subtitle of this is actually pretty important. I want you guys to underline the word attraction. Anything that I underline or circle, I want you to do as well. And you can certainly use a highlighter if you want to and just underline it, or you can highlight it, but you're going to need a writing utensil as well. So the role of attraction, I underlined the word attraction, and I remembered that we're talking about attraction between the molecules. So go ahead and write that. Attraction is between the molecules. And I'm going to keep going. If you need to stop it so that you can write your annotation, please do that. But I'm not going to tell you always to stop. Just do it when you need to. So the first thing is the topic sentence is actually pretty important in this paragraph. It says liquid oxygen is much harder to find than liquid water because oxygen molecules aren't strongly attracted to other oxygen molecules. Interesting. Those oxygen molecules are not strongly attracted to each other. They don't like each other. They don't want to be close to each other. So that's why it's a lot harder to find. So every substance has a certain level of attraction between its molecules that pulls the molecules towards each other. Think about that. Think about the pulling of molecules towards each other. That's the level of attraction. I want to make sure that I remind myself, if I want to use the abbreviation LOA, that's level of attraction, and then I'm reminding myself of the magnetic marbles that pulled together. In the video that we saw that if they had a weak LOA, a weak level of attraction, low level of attraction, their freedom of movement was high. And that is what you guys had written down on your pop quiz on that table. If they had a high level of attraction, then that means their freedom of movement was very low. So the stronger marbles on the right had a higher level of attraction, and they just kind of moved together as a solid the whole time. So this molecular attraction is stronger in some substances like water than it is in other substances like oxygen. Molecules in liquids and solids stay close together because of the attraction between the molecules. In the gas phase, molecules are able to move away from each other because they have a lot of kinetic energy, but attraction between the molecules still keeps them in the same general area. Different substances have different levels of attraction, but the level of molecular attraction for any one substance is always the same. That little last sentence there needs some annotation. Let me just kind of write down what it was saying. It was saying the level of attraction for oxygen is always the same, and the level of attraction for methane is always the same. But the level of attraction for oxygen and methane is different. See? Different substances have different levels of attraction, but the level of molecular attraction for any one substance is always the same. Since attraction never changes for a substance, something else has to change before the substance can change phase. That's really important. Something else has to change before the substance can change phase. And I wonder what that is. What causes level of attraction to increase or decrease? If it always stays the same, no matter what, if each substance has its own level of attraction, what causes that level of attraction to increase or decrease? So you can think of each substance as always being in a game of tug of war at the molecular level. This is a good question for us to ask. What causes level of attraction to increase or decrease? Next paragraph. Attraction is always pulling the molecules together, while kinetic energy allows the molecules to move around. So I circled these two because, just like what was in our quiz, these two, level of attraction and kinetic energy, they're kind of like that yin and yang, that tug of war. When something happens to one, it's going to affect the other one, as we're going to read in this paragraph. Substances change phase when either molecular attraction or kinetic energy wins the tug of war. And since each substance's molecular attraction is always the same, the change must be in the amount of kinetic energy the molecules have. So that's where the change comes from. Level of attraction is never going to change. It will on its own. It won't ever change on its own because each substance has its own certain level of attraction. However, when kinetic energy changes, then that will cause the level of attraction to change. So this whole last paragraph, don't highlight the whole thing because it's like if everything is highlighted, nothing's important. Go ahead and draw a box around that. And then we're going to write some annotations off to the side. So it says a large increase in kinetic energy. And notice that it says a large increase. Remember in the sim, if you just increase kinetic energy by 1 or 2 pushes, it didn't really change that much. So it has to be a pretty significant increase in kinetic energy. That can move molecules so fast that they overcome the pull of attraction and they move away from each other. Think about your marbles. When you added more kinetic energy to those weak marbles, they broke apart. The level of attraction was overcome. And then the opposite is also true. A large decrease in kinetic energy allows the attraction to overcome kinetic energy and it pulls the molecules towards each other. So, again, remember those weak marbles. When you guys were shaking them really hard and all of the marbles were bouncing around in that plastic container, as soon as you stopped adding kinetic energy, those marbles came back together. Not always, but they usually came back together and kind of formed that circle again. So let's just write a couple little annotations off in the margin, okay? First of all, I want to talk about the relationship between kinetic energy and level of attraction. And notice that I don't have that level of attraction causes a change in kinetic energy. It always has to be a change in kinetic energy will cause a change in the level of attraction. And it is inversely proportionate, meaning if one increases, the other one's going to decrease. So if kinetic energy increases, then the level of attraction will decrease. So this is exactly what we wrote down in that table, the graphic that you guys had from your pop quiz. And then conversely, if kinetic energy decreases, if the molecules slow down, then the level of attraction will increase and all those molecules want to cling closer together. And then this is how a phase change occurs. Okay, so for oxygen to change into a liquid, the attraction that pulls the molecules of oxygen towards each other must overcome the kinetic energy that pulls them away from each other. So we're talking about we're changing a gas to a liquid, so that's evaporation. So what it's saying here is it gets kind of wordy, so that's why I've got these annotations. It's easier for me to say, okay, evaporation means kinetic energy. Is that right? For a gas to change to a liquid. Oh boy, that's not right. I'm changing that right now. Sorry, you guys. That's not evaporation. That's condensation. Good grief. Okay, so then kinetic energy, let's see, for oxygen to change to a liquid, the attraction that pulls the oxygen molecules towards each other must overcome the kinetic energy. Yes. So that means that the kinetic energy decreases and then the level of attraction increases. So the gas molecules that are moving all over the place come closer and closer and closer and closer and closer together until they glide past each other. Let's keep reading the paragraph. Because the attraction between oxygen molecules is weak, a great deal of kinetic energy needs to be removed from the oxygen by making the oxygen very cold before their attraction can pull the molecules towards each other. Okay, down below you see these graphics, and you guys listen to me very carefully. If you remember in the pre-unit assessment, there's many questions on the test that describe and compare a substance A to a substance B, and it will describe maybe the phase or the state of matter that the substances are in. I want you guys to get used to identifying. I'm going to give you scratch paper tomorrow so that you guys can write down some notes as you're reading. Um, because it gets all very kind of confusing sometimes. And so I'm going to model for you how I want you to keep track of what you're reading. So we have this picture of substance A, we have a picture of substance B. Immediately I look at the dotted lines and I notice the key to the right. And I say substance A has these little teeny tiny small little red dots between the molecules. And that means that they have a weaker attraction. And substance B, their molecules have a stronger attraction. And it's also interesting to me that the weaker attraction for substance A, those molecules are farther apart, and the molecules for substance B are closer together because they do have a stronger attraction. So I'm reading the caption down below, and it says substance A is a gas and substance B is a liquid. I want you right now to annotate, and let's write that down. And this is what you're going to do tomorrow on your mid-unit test. You're going to write substance A is a gas and substance B is a liquid. And I want you to think about, I want you to think about the kinetic energy and the level of attraction for each one. So substance A is a gas. I'm going to label it a gas. It says they are the same temperature. Why is one a gas and one a liquid? Well, substance A has a weaker attraction, and its molecules have enough energy to overcome the attraction between the molecules and fly apart. So if I look at the kinetic energy and the level of attraction, remember they are inversely proportionate. In order for these gas particles to be moving so quickly and the temperature to be so much higher, then that kinetic energy has to be greater than the level of attraction. And so then when we say substance B has a stronger attraction, so substance B is a liquid, I'm going to label it liquid, and then I'm going to say it has stronger attraction. Its molecules don't have enough energy to overcome the attraction between the molecules. Therefore, the molecules stay together. So I know if I'm looking again at the inversely proportionate relationship between kinetic energy and level of attraction, the kinetic energy has to be less than the level of attraction. It has to be lower than, or I would say lower than the level of attraction. Okay. All right, let's move on. On the next page, you have a really beautiful picture of oxygen, and unfortunately, yours is black and white, so I wanted to show it to you in color. So, oxygen is pale blue when it's condensed into a liquid. I just think that's pretty cool. Notice the handler is wearing gloves because this liquid oxygen is incredibly cold, very, very cold. All right, so let's take a look at the paragraph. It says using attraction to make liquid oxygen. I'm going to tell you, we're not going to have as much annotations here because there's just, let's just read it, okay? Scientists use their knowledge of attraction to produce liquid oxygen. They know that they need to allow the weak attraction between oxygen molecules to pull them together. So remember, on our planet, oxygen exists in its natural state as a gas. It doesn't like each other. The oxygen molecules do not have strong level of attraction. They're very weak level of attraction. So in order to overcome that, they need to slow the molecules down. They need to decrease the kinetic energy. So it says they do this by transferring energy out of the oxygen, lowering the temperature of the oxygen molecules until their kinetic energy is so low that it can't overcome the attraction between the molecules. So we need to get that kinetic energy. We need to transfer the energy out. That lowers the temperature and it will allow those molecules to come together. So if we decrease, we're going from a gas to a liquid. If we decrease, then we're going to decrease the temperature. Remember, kinetic energy and temperature are directly proportionate. And then the level of attraction is indirectly proportionate, so that is going to increase. So, let me come back. I don't want to write that down yet. Let's keep reading. The temperature required to turn oxygen gas into liquid is far colder than what's required to turn water vapor into liquid. That's why oxygen needs to be extremely cold to change phase into a liquid, while water doesn't need to be very cold at all. All right. Want to know what the temperature? This is just a side note. You don't need to write that. The condensation point for water vapor is 100 degrees Fahrenheit. So it's really not that cold at all. Isn't that interesting? 100 degrees we feel like is hot, but remember, if the energy is being transferred out, it's going to start to condense. So not all substances have the same level of attraction. So it may take longer to increase or decrease kinetic energy. That's why, thinking back to the sim, you have to push those, add more energy or remove more energy, take away more energy. You have to push those plus and minus buttons multiple times. It takes a large change in order to overcome that level of attraction, or to like decrease kinetic energy, increase kinetic energy, which causes the molecules to either be pulled together or to come apart. Okay, when scientists need liquid oxygen, they can get it by separating oxygen molecules right out of the air. Air is a mixture of nitrogen and oxygen combined with small amounts of other gases like water vapor and carbon dioxide. Since the gases in air have different levels of molecular attraction, scientists can separate them by sending the air through a machine with different tanks that are at different temperatures. I'm just having you guys underline this again, that gases in the air have different levels of molecular attraction. And so they can separate them by sending them through the machine with different tanks that are at different temperatures. And I'm going to explain that graphic here in a second. So this is a liquid oxygen machine, and this is actually really cool. If you're on a spaceship, let's say you're on a space shuttle and you are launching into orbit, this is kind of something that they use in that machine, in that engine. Whereas if they need the in tank number one, we've got nitrogen and oxygen gas. Okay, so the tank is cooled, and that water vapor is it will it condenses into liquid water, and that liquid water is drained away. Okay, and actually, here's the thing. Let me just read what happens in the article, and you guys can just refer back to this as we're reading. Okay, so just let me familiarize yourself with this. We've got tank number one, and then we've got tank number two that's got liquid nitrogen and oxygen, and then tank number three. And I'm just going to let you guys refer back to that as we read. Okay, all right. So in the first tank, scientists decrease the temperature enough to condense the water into a liquid. That is, they decrease the kinetic energy of the molecules so the attraction between them can pull the molecules together. The liquid water that forms in the first tank is drained away, and then the remaining gases are put into a second tank and cooled below negative 183 degrees Celsius or negative 297.4 degrees Fahrenheit. That's cold enough that the molecules in those gases have very little kinetic energy to push the molecules apart. So again, we're talking about in that first tank condensation, gas to a liquid. I'm just repeating what we did before. So condensation means kinetic energy has to decrease, which decreases the temperature, and then the level of attraction increases and we go from a gas to a liquid. So in that second, oh, I'm sorry. Okay, whatever. Very little kinetic energy to push the molecules apart. Oh, let me read the last little part of this. Because of this, the attraction between the molecules pulls them together and condenses the gases into a liquid just like the water in the first tank. This liquid contains the molecules from the remaining gases in the air, including oxygen. The liquid mixture is then moved into a third tank that is heated up. Oh, now that's heated up. So you guys should know immediately, as soon as you say, okay, there's an increase in temperature, the reason why there is an increase in temperature is because the kinetic energy was increased. And that continues in that article to say that it's heated up just a little so the nitrogen evaporates. The kinetic energy of the nitrogen becomes too strong for the attraction between the molecules and they escape into gas. When the nitrogen evaporates, the liquid left behind is mostly oxygen. So, what's happening here is we're heating up the temperature. The reason why the temperature was increasing is because the kinetic energy increased. So, then what happens to the level of attraction? The level of attraction decreases. And of course, that's called evaporation, which is a liquid to a gas. I know it seems kind of confusing with this whole idea of the machine and the three different tanks, but it's just a really easy way to remind ourselves that, different substances can go between different phases just by increasing or decreasing kinetic energy. Fascinating. All right, let's continue. Last one. Oxygen isn't the only substance that's hard to condense because of weak attraction. Hydrogen and, look at this, methane also have very weak attraction. They like to exist on Earth as a gas, and so they're difficult to condense. And I wrote on there, they're difficult to freeze. We understand that because even though Titan is really, really cold, it was a liquid and then it was a gas. It's really hard to pull those level of attraction. Methane molecules don't like each other. They have weak attraction. Like oxygen, these are substances we tend to think of only as being gases on Earth. However, also like oxygen, they can become liquid if they're cooled enough. Cooling these substances just a little won't cause them to condense. These gases reach extremely cold temperatures because the kinetic energy is decreased before condensing into liquids. It's all about the attraction. And I just wrote a note. You guys don't know this. I made a mention of it before, but I'm thinking ahead to our liquid nitrogen lab because nitrogen exists as a gas, but we're going to be using liquid nitrogen. And so you can imagine the kinetic energy in liquid nitrogen is incredibly low. And so the level of attraction for those nitrogen molecules is increased. And that's how we get it to be a liquid. Okay, so here's an important idea from the reading. We talked a lot about molecular attraction. Molecular attraction is a pull between the two molecules that is always the same for a substance. We talked a lot about that back here in this article. I want you guys to hang on to the article. I'm going to be walking around tomorrow checking your annotations. If you did not list your annotations, you didn't copy what I have, you can do more if you want to. If there's other things that you need to write down, please, I hope you felt free to do that. But I'm checking to make sure that you did at least what I had. Okay? All right, so I want you to think about and connect what you read back to the water and the rubbing alcohol investigation. Why do you think that in only 5 minutes, the isopropanol or the rubbing alcohol completely evaporated, but the water did not? They're both liquids. They're both clear. Why did the rubbing alcohol evaporate from a liquid to a gas faster than the water did? Remember, it all has to do with the level of attraction. Let me ask you this question. Which molecules have a stronger level of attraction? Water or isopropanol? Which ones want to stay closer together? I hope you said water. I hope you did. We're going to come back to this in a second. Okay, the key concepts on the next 2 slides can help us to understand and explain the ideas that we just learned about molecular attraction and phase change. So we're on key concept number 9, and I've added these bold and underlines just to help you identify the important words here. So key concept number 9 says whether or not a phase change occurs is determined by the interaction between the kinetic energy of the molecules and the attraction pulling the molecules together. So what you're saying is phase change depends on the interaction between kinetic energy and attraction. And remember, they are inversely proportionate. If kinetic energy increases, level of attraction is going to decrease, and vice versa. Key concept number 10 just says the molecular attraction of a substance never changes. The molecular attraction of water is always going to be the same no matter what. The molecular attraction between methane is always going to be the same no matter what. The only thing that will change it or cause it to increase or decrease is if it is reacting to an increase or decrease in kinetic energy. So let's come back here to our water and isopropanol and find out. Phase change does not happen every time the kinetic energy of a substance changes. This is because phase change is determined by both kinetic energy as well as molecular attraction. There's stronger molecular attraction in water. The water molecules want to stay together, and so we have to have more kinetic energy to overcome that level of attraction for it to break apart. The isopropanol alcohol, the rubbing alcohol, has weaker level of attraction. What that means is it doesn't require as much kinetic energy to overcome the level of attraction. I hope you all understand that. If you don't understand that, please send me an email, um, and I will get back to you and answer your questions, okay? So, now one last thing. I want you to make some connections between the article that we read and the simulation. We're going to think about the chapter question, why didn't the liquid methane change phase before 2007? And then later, you're going to be writing an explanation to address this question. So let's start by examining the representation of Titan summer on the next slide. So remember, Titan summer started in 2002. It was summer for 5 years when the photo was taken in 2007 and that methane lake was liquid. And then at some point in time after that, the liquid lake evaporated and became a gas. So why didn't the liquid methane change phase before 2007? We know that the lake evaporated sometime during that, but we also know that it hadn't evaporated in 2007 because we have a photo of the liquid lake in 2007. So something happened in the summer around 2007 to cause the lake to evaporate. How can we explain why the lake didn't evaporate before 2007 and why did it evaporate after 2007? Our experience with the sim showed us that the answer to the chapter question has something to do with a molecular attraction. So let's look at another example from the sim to help us think about molecular attraction and phase change. So this evidence from the sim shows substance A, and remember substance A is a solid at 36 degrees Celsius. Okay, it is a solid. This evidence from the sim shows the substance A at 206 degrees Celsius. And at this temperature, substance A is still a solid. So we are increasing kinetic energy, but it takes a lot of kinetic energy before substance A will change phase from a solid to a liquid. So at 206 degrees Celsius, substance A is still a solid, even though enough energy was transferred into substance A to increase the kinetic energy of the molecules and raise the temperature by more than 200 degrees Celsius. But here's the key, you guys. The freedom of movement and the phase did not change. What's causing I will just say this. The level of attraction of substance A is so strong. We need a lot of kinetic energy added in before that level of attraction can be overcome. Does that make sense? The evidence from the sim shows that energy can be added to a substance without the substance changing phase. I'm going to say that again. The evidence shows that that kinetic energy can be added to a substance without the substance changing phase. So think about the example of substance A, and now think about why don't you think the liquid methane, I didn't say that right. Why do you think the liquid methane didn't evaporate before 2007? So now this is what substance A looks like when the temperature is over 400 degrees Celsius. Enough energy has been added to change the freedom of movement. And at this temperature, substance A changes phase and it becomes a liquid. So think about what happened to substance A at 400 degrees Celsius. And how can this help you explain what happened to the lake after 2007? I've got a couple more key concepts to show you on the next 3 slides that help explain these ideas about how molecular attraction, freedom of movement, and phase change are related. So key concept number 11 says a phase change occurs when the kinetic energy increases enough to overcome the attraction between the molecules. Again, really pay attention to the bolded and the underlined. Those are the key words. Kinetic energy has to increase enough to overcome attraction before a phase change can occur. Key concept number 12. A phase change occurs when the kinetic energy decreases enough so that the attraction pulls the molecules together. And then lastly, different substances can have either weaker or stronger molecular attraction. So just a reminder, tomorrow you guys are going to have a mid-unit assessment. I'd like you to study this because this will be a part of that. Again, if you score in the 90th percentile, you can move on. I know that there are quite a few of you guys that scored as a PB2 in the pre-unit assessment. And so I kind of am anticipating that you guys are, I'll have a number of people moving on. So just go ahead and make sure that you're able to fill this in. The worksheet is going to have the arrows on it, but it will be blank. There's nothing written on it. You're going to have to write it in. And then you get to use this on your test to help you just kind of keep track of what the questions are asking. Okay. The last thing I'm going to tell you is this. You have a homework assignment. In today's folder in Schoology, you have a PDF titled Lesson 3 Homework. And the question is just asking you, this is not a scientific argument, okay? Let me repeat, this is not a scientific argument. You do not need to use race to answer this question, but I need you to use complete sentences. And I also have some words in the word bank that I want you to use. So the question is, why didn't the methane lake, here's the question, why didn't the methane lake change phase before 2007? It's right up here in the top. So you need to kind of let me know what's going on. You might, you clearly state how or why something happens. Use terms like because, therefore, since, and this. And write important cause and effects. Use these word banks, the words in the word bank. You can think about the article, think about what you saw in the sim, think about the molecular or the magnetic marbles, think about the isopropyl, the rubbing alcohol in the water. We had a lot of examples today. You can use any of those to help explain the answer to your question. Okay. Now I just have one page here. If you need to use the backside in your writing, you certainly can do that. Whoa, so sorry. But you're going to go ahead and just copy this in GoodNotes and you can type up your answer. I do have some hard copies available if you'd like a hard copy. Chances are you're probably watching this video after science class, so you didn't pick up a hard copy, and that's okay. Just go ahead and put this in GoodNotes and type up your answer, okay? Let me know if you have any questions. You guys have been awesome. This was a long video, big lesson. I appreciate your attention, and I will see you tomorrow.